This is my intermediate algebra course. Today we're going to continue to learn transformations and the library of relations. If you haven't done the homework completely incorrectly from the last class, do that homework before watching this video. In the previous classes, we reviewed transformations and introduced the idea of a relation. You can review that information here if you'd like. You're going to need the library of relations, which we introduced again in previous classes. Take a picture with your phone. You're going to need this library right in front of you as we work along in the class today, as in the previous classes. If you want to look for the library online, it's going to be called the library of functions. You'll also need the transformation properties at the right. And here's the remaining transformation properties, so make sure you have those right in front of you as we work along today. In the previous classes, we graphed equations. And in every case, when I gave you an equation, I wrote it in a particular form, so you could see exactly how to transform the parent graph. But in most cases, when you're given an equation, it's not going to be in that exact form. So what we're going to do today is we're going to learn how to alter equations so that we can recognize how to transform the parent graph to graph those equations. So let's start with this problem here. We know that if we subtract 2 from x, we move the graph of the previous equation 2 units to the right. But we're not subtracting 2 from x. We're subtracting 2 from the absolute value of x. If we subtracted 2 from x in the absolute value of relation, it would look like this. This purple equation tells us to move the parent graph 2 units to the right. But again, we're not subtracting 2 from x inside the absolute value. We're subtracting 2 from the absolute value of x, which is different. So we need to alter the form of this equation. So what I'm going to do is I'm going to add 2 to both sides of that equation. And what that's going to do is it's going to put the 2 on the other side of the equation, because these 2's are going to cancel out, and we get y plus 2 is equal to the absolute value of x. It's very important to understand that this yellow equation up here is the exact same equation that you see in blue. The only difference is the form. We changed the form. If you graph the yellow and the blue equations, you'll get the same graph. Again, because they're the same equation. But the blue equation shows us how to graph the equation, because we see that subtracting 2 from the absolute value of x in this equation is the same thing as adding 2 to y. So now we know to take the parent graph and just move down 2 units. So we're ready to graph. Let's write the equation of the parent relation. Whenever you draw a graph, you need to write the equation either above the graph or on the graph somewhere. And let's go ahead and draw that now. If you have your library of relations right in front of you, you know that this is just the V shape. And you've graphed this enough to where you probably don't even need the library in front of you, but you should have it just in case. So this is the parent graph, and now again this graph, or this equation here, tells us to move down 2 units. So let's take this reference point 0, 0, move down 2, and all the other points are moved down 2. So we have the graph of the equation. And there you go, it's that easy. So the equation that we graphed, the final answer is y plus 2 is equal to the absolute value of x. And maybe we'll write that in orange, because that's technically a translation. So this may not seem like it's very important, but actually this lesson is going to be extremely important, because if you don't know how to recognize what types of transformations are occurring on the parent graph, then everything we learned in the previous classes is for nothing. Again, in most cases, when you see an equation written, it's not going to be written in that particular form that shows you what to do to the parent graph when using the transformation method. So it's extremely important that you learn how to alter equations so that we can see exactly how to graph them. Now, before we continue, I want to mention this work here that I demonstrated to explain how we move the 2 to the other side of the equation. You don't have to show that work. The reason that I'm demonstrating this basic operation here is that I just want to be absolutely clear what's happening. This is an intermediate algebra course, which means that, again, you don't need me to demonstrate that or to write that for you. That's pre-algebra stuff. But I'm going to show that work in every step because I want you to be, again, absolutely clear what's happening in these problems. Okay, let's go on to number 2. You know that when you add 1 to x in an equation, you move the graph of the previous equation to the left 1 unit. The problem is we're not adding 1 to x here. We're adding 1 to x cubed. If you added 1 to x with this parent relation, it would look like this. This equation here tells you to move the cubic relation, the graph of the cubic relation, to the left 1 unit because we're adding 1 to x in yellow. But in this situation, we're not adding 1 to x. We're adding 1 to x cubed. It's not the same thing. So we're going to do the same thing that we did in the previous problem. We're just going to put that 1 on the other side. So we're subtracting 1 from both sides, and we get y minus 1 is equal to x cubed. So again, the graph of this yellow equation is the same graph that you get when you graph the blue equation. The equations are just in different forms, but now down here in blue we can see what to do to the parent graph. I know this seems easy, but it's so important that you understand these principles because, again, everything we learned in the previous classes is going to be useless unless you know how to change the form of equations so that we can recognize how to graph them. So let's draw the parent graph. We have the parent equation I just drew there. So this is the cubic relation. So there's the parent graph. Now, before I forget, I'm going to go ahead and write the equation, the altered equation, which is the same equation we're trying to graph up here. And so we're subtracting 1 from y, so that tells us to move the blue graph down, or actually up 1. So we move up 1. And I think if we plug in 2, 1, 2, we'll go down 1, 2, 3, 4, 5, 6, 7, 8. So we just barely make it on the graph. Now again, you can use this equation to find that extra point, or you can use this equation. If you use this equation, you have to pretend that this is the origin. It's not the origin. If you use this equation, then you would have to plug in -2 to x and then solve for y to figure out where y is going to be. So there you go. Okay, so let's try a couple more of these. Actually, I think we're going to try one more of these before you try one on your own. You know, again, that when you subtract 4 from x, you move the graph of the previous equation 4 units to the right, but we're not doing that. If you subtract 4 from x, starting from the parent relation, you would you would see this equation here. This means move 4 units to the right. But we're not doing that. We're subtracting 4 from 1 over x. It's not the same thing. So what we're going to do is we're going to add 4 to both sides of the equation. And that's going to cancel out the 4's on the right side. And now we have this different form, and obviously you can see that tells us to just move the graph down 4 units. So let's write the parent relation. So the parent relation is going to require some asymptotes. Remember, this is the reciprocal relation, and the reciprocal relation has 2 asymptotes. And then we have our reference points: 1, 1, 1/2, 2, 2, 1/2, -1, -1, -2, -1/2, and -1/2, -2. Those 6 reference points are always the same for the parent reciprocal relation. The parent graph for that relation. So now we're moving down 4 units. So 1, 2, 3, 4. So our horizontal asymptote is going to be down here. The vertical asymptote doesn't change positions. And before I forget, I'm going to write the equation of the equation that we're trying to graph. And our reference points just move down. So we have, if we're assuming this is the or pretending that this is the origin, we have the same reference points: 1, 1, 2, 1/2, 1/2, 2, -1, -1, -2, -1/2, and -1/2, -2. Connect the dots. And there you go. All right. So now it's time for you to try. You can take a picture of all these problems that we did if you'd like. I want you to try number 4. If you add 2 to x with this parent equation, it would look like this. That's adding 2 to x. Then you'd move that parent graph 2 units to the left, but we're not doing that. We're adding 2 to the square root of x. So you have to put that 2 on the other side of the equation. Then you can see how to transform the parent graph. So go ahead and try number 4. Do your math here and write your altered form. And remember to write the forms of the equations above the graphs, starting from the parent graph. Try number 4. When you come back, we'll do it together. All right, we're back. Okay, so we're going to subtract 2 from both sides of that equation. And then we get y minus 2 is equal to the square root of x. And so now we can see how to graph it. Let's write the parent equation. And looking at your library, you know 0, 0, 1, 1, and 4, 2 are reference points we can use to graph the parent graph. And this is a translation, so I'm going to use orange because we're used to using orange for translations. Not that it really matters. And we're subtracting 2 from y. We see that the only difference between this equation that we're trying to graph and the parent equation is we're subtracting 2 from y, so we just move up 2. Now again, I know this seems like it's a little easy. After all the difficult equations that you've graphed, you're probably thinking, well, why are we doing this? It just seems too easy. Well, again, we're starting out with very simple problems, and we're going to get more and more difficult. But it's very important that you know the principles here, or else you're going to have a lot of trouble when you try to graph equations that are not in the proper form. So if you got that one right, good job. Okay, go ahead and try number 5. And when you come back, we'll do it together. All right, we're back. When you subtract 5 from x in an equation, you move the graph of the previous equation 5 units to the right, as in this situation here. But we're not subtracting 5 from x. We're subtracting 5 from x squared. That's not the same thing. So let's take this equation and change the form. Let's add 5 to both sides of the equation. And then we get y plus 5 is equal to x squared. Well, now we can see what to do to the parent graph. So the parent equation is y is equal to x squared. And look on your library, you see we have these reference points. We've drawn these graphs many, many times. And the only difference between the parent equation and the equation that we're trying to graph is we have y plus 5 instead of y. So that tells us to move the graph down 5 units. So as you can see, this is really not difficult, but it's an extremely important topic. Now we need to fill our window here, so I'm going to pretend that this is the origin down here, and I'm going to use this equation. So if we plug in 3, we get 9 into this equation, if you plug in 3 to x. So pretending that this is the origin, I'm going to go 1, 2, 3 to the right, and 1, 2, 3, 4, 5, 6, 7, 8, 9 up. So that helps us to fill up our window. Remember, you always have to fill up the window completely on your graph. So if you got that one right, good job. I want you to try number 6. Number 6 is going to require an asymptote, a horizontal asymptote. Try number 6, and when you come back, we'll do it together. All right, we're back. Again, we're not adding 1 to x. We're adding 1 to 3 to the x. So we have to change the form of the equation. So we're going to subtract 1 from both sides. And then we get y minus 1 is equal to 3 to the x. And now we can see how to graph this equation. And so remember, an exponential relation has a horizontal asymptote on the x-axis. And before I forget, let's draw the parent equation first. So we can use this equation to help us. Plug in 0, we get 1. Plug in 1, we get 3. And that's about all we can do for the parent graph. And now we're going to graph y minus 1 is equal to 3 to the x. And that's going to move the asymptote up 1 unit, because when you subtract 1 from y, you move the graph up 1 unit. And we just move all the points up 1. And there you go. It's that easy. So if you got that one right, excellent. So now let's try number 7 together. Now, this is a source of potential problems. A lot of students will look at this and they'll say, well, we're adding 4 to x in this equation, so we just take the parent graph, which is the graph of y is equal to log base 2 of x. We just take the graph of that equation and move it to the left 4 units, because we're adding 4 to x. But we're actually not adding 4 to x. We're adding 4 to log base 2 of x. Now I know you're going to say, nope, I can see it right in front of me. We're adding 4 to x. If you're adding 4 to x, you would need parentheses. You see, it's all part of the notation. In the English language, for example, there are certain rules that you have to follow, and we may not like the rules, but they're just the rules, and there may not even be an explanation. It's just what people decided the rules are going to be. And with math, mathematicians decided that you need parentheses if the 4 is actually going to be added to x. We're not adding 4 to x, we're adding 4 to log base 2 of x, so there are no parentheses. So you have to consider this number here and this expression here to be separate terms that you're adding together. So we have to change the form of this equation. We're going to subtract 4 from both sides, just like we did in all the other problems. And then we get y minus 4 is equal to log base 2 of x. Now, you know that if you have a logarithmic graph, it's going to have a vertical asymptote, and we can use these logarithm properties at the bottom to help us. We're going to use logarithm property 9 to find the point 1, 0. That's actually a point that's always on a logarithmic parent relation, regardless of the base of the logarithm. Then we're going to use this property down here, logarithm property 3. We're going to plug in 2 for x, and we get 1. Then we're going to use this middle logarithm property, and we're going to plug in powers of 4 for x. We're going to plug in, or excuse me, powers of 2, not powers of 4, powers of 2, because the base is 2. So 4 is a power of 2. 4, let's write it over here just so we can be clear what's occurring here. If we plug in 4, don't you agree that 4 is the same thing as 2 to the second power? So I plugged in 4 there, but that middle logarithm property tells us that the value of this logarithm has to be whatever that exponent is. That's just that logarithm rule. So you plug in 4, 1, 2, 3, 4, you get 2, and that's about all we can do as far as the points on the parent graph. So now we're going to graph y minus 4 is equal to log base 2 of x, and that means we're going to move the whole graph up 4 units, but that's not going to change what the asymptote looks like. So 1, 2, 3, 4, all of these points just move up 4 units. And there you go. So now we can connect the dots, and we have our graph. Okay, so I want you to try a problem like that. You can take a picture of these with your phone if you'd like to use those. Again, we're not subtracting 1 from x. We're subtracting 1 from log base 3 of x. So go ahead and try number 8. You got to put 1 on the other side of the equation. When you come back, we'll do it together. All right, we're back. So we're going to add 1 to both sides of that equation so we can put it in a form where we know how to graph it. So we now have 1, or y plus 1 is equal to log base 3 of x. And let's graph the parent equation. So again, we have a vertical asymptote. And if we use the logarithm rules, we plug in 1, we always get 0. We plug in 3. 3 is the base, so if you plug in 3 for x, you always get 1. And then we need to plug in powers of 3, but 9 is the next power of 3, which means that it's not going to be on our window. So we can just connect the dots. And then we're going to graph that equation y plus 1 is equal to log base 3 of x. And of course, we just move down 1 unit. So we just take all the points that we graphed in the previous graph and move down 1. Connect the dots, and there we go. So if you got that one right, excellent. Okay, let's go on to number 9. You know that when you divide x by 2 in an equation, you multiply all the x values of the graph of the previous equation by 2. But in this situation, we're not dividing x by 2. We're dividing x squared by 2. It's not the same thing. If you divide x by 2 in this parent graph, you would need parentheses. Now, it doesn't look like it's much different from this blue graph over here, but they're very, very, very different. Again, with math, it's these little details that tend to make things difficult. So what we're going to do is rewrite the equation. We're going to multiply both sides of the equation by 2. Now you can use a dot for multiplication, you can use parentheses. Over here we don't really need either. We can just write a 2 next to the y. And because x squared is divided by 2, when you multiply by 2, you just cancel out the 2's on this side, and you end up with 2y is equal to x squared. So now we can see that dividing x squared by 2 is the same thing as multiplying y by 2. I know that seems weird, but we're going to write the parent graph as usual. Use our reference points. You should have the library right in front of you. And the new graph, this is dilation, so I'm going to use purple. You don't really have to use colors, but that's just the color we used for dilation in the previous classes. And so multiplying y by 2 tells us that we're going to take all the y values of the previous graph and divide by 2. So if you do that, you get the following graph. We're going to need to fill up our windows, so I'm going to plug in 3 for x. If you plug in 3 for x and solve for y in this equation, you get 4.5. So that gives us these points here. And then we can connect the dots. And we have our graph. Okay, so let's try a couple more of these before you try one on your own. Now, this is a situation that, again, really plagues students. For some reason, students have a lot of trouble, and I'm sure I had a lot of trouble when I learned this too for the first time, but they have a lot of trouble understanding that the yellow 3, when it's written next to a square root symbol, that means 3 times the square root of x. We're multiplying the yellow by the blue. That's what that means when you write a number right next to a square root. Again, a lot of students have trouble with that. So we're not multiplying x by 3. If you multiplied x by 3 in the parent equation, the 3 would have to be inside the square root. This means that you divide all x values in the previous, or the graph of the previous equation, you divide all of them by 3, all the x values. But we're not doing that. We're not multiplying x by 3. We're multiplying the square root of x by 3. It's not the same thing. So I know that I sound like a broken record here, but it's so important to get these basic principles. So what we're going to do is we're going to divide both sides of the equation by 3. So the altered form of the equation is going to be y over 3 is equal to square root of x. Now we know to multiply all the y values in the graph of the parent equation by 3 in order to draw the graph of the equation that we're looking for. So let's start with the parent relation. We've seen it quite a few times. It's the square root parent graph. And now let's use purple for dilation. We're dilating. And so we're going to multiply all the y values in the graph of the previous equation by 3 because we're dividing y by 3. Remember, it's the exact opposite of what you would think. So we have 0, 0, 1, 3, and 2, 6, or actually 4, 6. Then we just connect the dots, and there you go. Okay, let's try one more of these. Obviously, we're not dividing x by 4. We're dividing 2 to the x power by 4. So we don't know what that does to the parent graph. So we're going to have to rewrite the equation, and we're going to multiply both sides of the equation by 2. Actually, multiply by 4, sorry. Multiply both sides of the equation by 4, and that's going to cancel out these 4's here. So we get 4y is equal to 2 to the x. Now we can see that what we're doing in this equation up here is we're actually just multiplying 4, or multiplying y by 4. So now let's write the parent graph. And this is a exponential relation. So we have a horizontal asymptote in the x-axis. 0, 1 is always a reference point we can use. Plug in 1 into this equation and we get 2. Plug in 2, we get 4. And that's about all we can graph without going outside of the window. So now we're going to graph the equation that we're trying to plot. And we know when you multiply y by 4, you just divide all the y values of the graph of the previous equation. So we're going to divide every point by 4. And that gives us these points here. And I think we're going to possibly need one more point, maybe a couple more. So let's try plugging in 3 for x in this equation. 2 to the third power is 8. Then divide both sides by 4, we get 2. So when you plug in 3, you get 2. So 1, 2, 3, and up 2. Let's try plugging in 4 to x. 2 to the fourth power is 16. Divide both sides by 4, and you get 4. So we plugged in 1, 2, 3, 4, and we go up 1, 2, 3, 4 to get that point there. And we can try maybe plugging in 5. I think that's going to go outside the window, though, so we can just connect the dots at that point. The position of the horizontal asymptote doesn't change. So there you go. Okay, so now it's time for you to try. You can get a picture of numbers 9 through 11 if you want to refer back to those problems. I want you to try number 12. It looks like we're multiplying x by 4. But if you were going to multiply x by 4 in the parent equation, the 4 would have to be inside the absolute value symbol. This means divide all the x values of the graph of the previous equation by 4. But we're not multiplying x by 4 as in this yellow equation. We're multiplying the absolute value of x by 4. It's not the same thing. So the transformation properties don't tell us what to do. So we have to divide both sides of the equation by 4, and we get y over 4 is equal to the absolute value of x. These 4's canceled out. So now we can see what to do. Let's graph the parent relation. You're very familiar with this parent relation by now. It's just the v. So connect the dots. You might think, well, I don't really need to graph these parent relations over and over again, but you do, because it's not enough just for you to be familiar with these graphs. You need to know them like the back of your hand. Okay, so now we're going to graph the altered form of the equation. Y over 4 is equal to the absolute value of x. When you replace y with y over 4, that just means you multiply all the y values of the graph of the previous equation by 4. So we're going to have 0, 0, and 1, 4, and negative 1, negative 1, positive 4, and any other points looks like they're going to be outside the window. Okay, there you go. If you got that graph, excellent. I want you to try number 13. You know that when you divide x by 5, you multiply all the x values in the graph of the previous equation by 5, but we're not dividing x by 5 here. We're dividing log base 4 of x. X is in the log function, so it's not the same thing. So go ahead and try number 13. Put that 5 on the other side of the equation, and when you come back, we'll do it together. All right, we're back. So we're going to rewrite that equation, and then we're going to multiply both sides of the equation by 5, and we get 5y is equal to log base 4 of x. And now we know how to use the transformation properties to graph that equation. Let's write the parent graph. We have a vertical asymptote, of course. We have the point 1, 0 using property 9 at the far bottom right. If you plug in 4, the base of the logarithm is 4, so if you plug in 4 for x, we get 1. That's logarithm property 3 down here. And I don't think we're going to be able to fit any other points on the window, so we can just connect the dots. This is supposed to be more of a smooth curve there, but okay, so now we're going to graph 5y is equal to log base 4 of x. That just means we divide all the y values in the graph of the previous equation by 5. So that's not going to change the position of the vertical asymptote. This point here is not going to change because the y value is 0. This point is going to go down The new y value of that point is going to be 1/5. So it's going to be pretty close to the x-axis. And those are the only points that really fit on the graph. So you can see that what happened, it was a vertical compression. We pushed down on the graph. Okay, if you got that one right, good job. I want you to try number 14. This is another type of problem that students really have trouble with. When you multiply x in an equation by 2, you divide all the x values in the previous graph by 2. And this is multiplying x by 2. But we're not multiplying x by 2, we're multiplying x cubed by 2. So you're going to need to get that 2 on the other side of the equation so we can see how to use the transformation properties to graph that equation. Try 14. When you come back, we'll do it together. Alright, we're back. So I'm going to divide both sides of that equation by 2. So we get y over 2 is equal to x cubed. Alright, so the parent equation is obviously y is equal to x cubed. It's the cubic relation. So you have your reference points on your library of relations. That's what the graph looks like, but we are going to graph y over 2 is equal to x cubed. So the only difference in that equation is that we have y over 2 rather than just y. So that tells us we're going to multiply all the y values in the previous graph by 2. Again, it's the opposite of what you would think. And there you go. So if you got that one right, excellent. All right, now the next problem is another source of confusion for students. For some reason, when students see a number multiplied into an exponential expression, they have a lot of trouble understanding what exactly is occurring there in the notation. The yellow 5 is multiplied by the blue 2 to the x. And you see this in different forms. Sometimes you'll see a dot in between the 5 and the 2, and that usually creates more problems for students because they try to multiply these and get 10. That's not proper math. You may see parentheses on the 5 instead of the 2. That's okay. But what this means is, we're multiplying 5 by the exponential expression. We don't know what to do in that situation, so we have to divide both sides of the equation by 5. So we're going to divide both sides of the equation by 5. That's going to cancel out the 5's on the right side of the equation, and now we can see that all we're doing is dividing y by 5 because the 5's canceled out. Because we're multiplying 5 by 2 to the x, when we divide both sides by 5, it just cancels out that operation. So the parent equation is obviously y is equal to 2 to the x. It's an exponential relation. The point 0, 1 is always a reference point we can use. Plug in 1, you get 2. Plug in 2, you get 4. And that is the parent graph. So now we're going to graph y over 5 is equal to 2 to the x. That means to multiply all the y values in the graph of the previous equation by 5. So we have the point 0, 1, that becomes 0, 5. And any other points out here are obviously going to be outside the graph. In this situation, we might want to plug in a negative number. We don't usually do that, but let's try plugging in negative 2. So if we plug in negative 2, remember 2 to the negative 2 power is the same thing as 1 over 2 to the positive 2 power. which becomes 1 over 4. So then we get y over 5 is equal to 1 over 4. Multiply both sides by 5, and we get 5/4. So if you plug in -2, we get 5/4. Okay, now let's plug in -1. If you plug in -1, you get 5/2, which is 2.5. And I think that's going to be enough points. I forgot to draw my asymptote. You want to probably do that first. Okay, so there you go. Now I want you to try number 16. Remember, when you have a 3 next to an exponential expression, or any number next to an exponential expression with parentheses or a dot, that means multiplication. So you're going to have to put that 3 on the other side. Try number 16. When you come back, we'll do it together. Okay, we're back. I'm going to rewrite that equation, and I'm going to divide both sides by 3, because 3 is multiplied. We have to do the opposite of multiplication. So then we have y is equal to 4 to the x power as the parent relation. Plug in 0, we get 1. Plug in 1, we get 4. Those are our points we can use to graph the parent relation. And the graph that we're trying to, or the equation we're trying to graph, is y over 3 is equal to 4 to the x. So we just take all the y values in the previous graph and multiply by 3. Remember, it's the exact opposite of what you would think. We multiply, we don't divide. So then we get, we may have to plug in a negative number over here. Let's try plugging in -2. Actually, let's plug in -1. 4 to the -1 is 1 over 4 to the +1, which is 1 over 4. Multiply both sides by 3, we get 3/4. So if you plug in -1, you get 3/4. That helps us to see where the graph is going. And I can't forget to draw my horizontal asymptote. Okay, so if you got that one right, excellent. Now this is kind of a special problem. Remember, when you divide x by 3 in an equation, you take the graph of the previous equation and you multiply all the x values. But we're not dividing x by 3 here. We're dividing 3 by x. This is dividing x by 3. We're not doing that. We're dividing 3 by x. So this is a really bizarre situation here. And what we need to do is we need to obviously change the form of the equation. So we're going to rewrite the equation. And I want you to be aware there's a lot of ways to do this. The easiest way to do this problem is just multiply both sides by 1/3. And you can use parentheses. You can do it any way you want. And there's a 3 in the top and a 3 in the bottom, and they're going to cancel out. Now, a lot of students don't like that. They're not used to that method. That's the easiest method. So when you multiply y by 1/3, you can write y as y over 1, and now we're multiplying fractions. When you multiply fractions, you just multiply the numerators. 1 times y is y, and the denominators. 3 times 1 is 3. So on the left side of the equation, we get y over 3. On the right side of the equation, again, we're multiplying fractions, so we just multiply 3 times 1, and we get 3. And 3 times x is 3x. But it's important to understand that those 3's will cancel out. And maybe I should leave some more room for that extra step so we can see exactly what's happening. So those 3's cancel out, the yellow 3's, and we get y over 3 is equal to 1 over x. So now, again, it's the same principle that we've been using. We couldn't graph y is equal to 3 over x, but now we can graph y over 3 is equal to 1 over x, because we see that we're just dividing y by 3. So remember, the reciprocal relation, which has a variable in the denominator, in this case x, it always has 2 asymptotes and those 6 reference points. We're going to connect the dots, and there you go. Okay, now we're going to graph y over 3 is equal to 1 over x. And that just tells us to multiply all the y values in the graph of the previous equation by 3. That's not going to affect the position of the asymptotes. So if we multiply all the y values, we get the following points. And we can just connect the dots. So there you go. So that's kind of an odd problem. Go ahead and take a picture with your phone, number 17. You can use that to help you on number 18. I want you to try a problem like that. Go ahead and try number 18. You need to multiply both sides of the equation by 1/2. And when you come back, we'll do it together. All right, we're back. So again, I'm going to rewrite the equation and multiply both sides by 1/2. Doesn't matter what side you put the 1/2 on. And then we get y over 2 is equal to 2 over 2x. You don't have to write that 2 over 2x. You can just cancel out the 2 in your head if you want to, but I'm going to show that step. So we end up with y over 2 is equal to 1 over x. So again, I know you just graphed this parent graph, but this is good practice. I want those 6 reference points. Again, you need to know these graphs like the back of your hand. So even though you're graphing the same parent graph over and over again, I want you to do it. It's very, very good practice. Okay, now we're going to graph y over 2 is equal to 1 over x. So we multiply all the y values in the previous graph by 2. That's not going to change the position of the asymptotes. So I'm going to redraw those asymptotes. And we have the following points. And we connect the dots. And there you go. So if you got that graph, excellent. Let's go on to 19. Now we're going to deal with reflections. If you write a negative on x, you reflect the graph of the previous equation across the y-axis. But again, you can see we have the same theme here. This is writing a negative on the x in an equation. This over here is writing a negative on the absolute value of x. It's not the same thing. So in this situation, you'd reflect the graph of or the parent graph across the y-axis. But we're not going to do that here because, again, the negative is not on x. It's on absolute value of x. Now, another source of confusion is when students see a negative in front of an absolute value symbol, they usually don't realize that the negative is multiplied into the absolute value of x. So this expression really means -1 times the absolute value of x. So what we have to do is we have to divide both sides of the equation by -1 in order to put the negative on the other side. So I'm going to divide both sides by -1, and we get -y is equal to absolute value of x. The -1's obviously cancel out here because we're multiplying -1 and then we're dividing -1, so it cancels out. And whenever you divide anything by a -1, it just changes the sign of the thing that you're dividing into. So the y just becomes -y. Same is true when you're multiplying by -1. Most of you probably know this, but just to make sure that students have this information reviewed. So the absolute value relation is the parent relation, obviously, and the graph looks like that. Then we're going to graph -y is equal to the absolute value of x. And you can see because because y is just replaced with -y, we're not reflecting across the y-axis, we're reflecting across the x-axis. We couldn't see that in the original equation. See this original equation up here? We couldn't see that we were reflecting across the x-axis. It almost looked like we were reflecting across the y-axis, but actually we were reflecting across the x-axis. Again, these are things that don't seem like a big deal, but if you don't understand how to work with these equations, you're going to have no chance to graph them. Okay, on to number 20. We have the same situation here. If a negative is written on x in this parent equation, or the corresponding parent equation, then you would need parentheses. So we don't have a negative written on the x, we have a negative written on x squared. And again, what that means is y is equal to -1 times x squared. You can write a parentheses on both or just one, but it's multiplication. So we're going to change the form of that equation by dividing both sides by -1. And that just changes the sign, so we have -y is equal to positive x squared. And so the parent relation is y is equal to x squared. You know what that graph looks like, of course. So we're going to plot that graph. And then we're going to plot -y is equal to x squared. When you replace y with -y, you reflect across the x-axis. So we're just going to flip the graph down. And there you go. Okay, let's try one more of these before you try one on your own. So we're going to divide both sides of that equation by -1. Because again, that negative is multiplied. This is -1 times the log base 4 of x. So log base 4 of x is the parent equation. We can use our log rules there. Plug in 1, you always get 0. Plug in 4, that's the same number as the base, so you get 1. And that's all we can fit on our window. So then we're going to graph negative y is equal to log base 4 of x. That reflects across the x-axis. So we get the following graph. And we can connect the dots. And there you go. Okay, on to number 22. Go ahead and try number 22. If you were going to write a negative on the x, you would have to put it inside the square root symbol. We're not writing a negative on the x, so we're not going to reflect across the y-axis. We have a negative written on square root of x, which means negative 1 times the square root of x. So we need to get rid of that negative 1 or put it on the other side of the equation. So go ahead and try number 22. You can reference these problems if you want to, or this problem to help you. So try 22. When you come back, we'll do it together. Alright, we're back. So I'm going to rewrite that equation, but I'm going to divide both sides by negative 1. The negative 1's cancel out. We get negative y is equal to square root of x. Now we know exactly what to do using the transformation method. We'll start with our square root parent relation, and we're writing a negative on y, so that tells us to reflect across the x-axis, and we get the following graph. So if you got that one right, excellent. I know it seems like what we're doing is pretty easy, but this is actually something that is really, really important for future math. So make sure that you're doing all these problems. Go ahead and try 23. When you come back, we'll do it together. All right, we're back. So the negative is not written on x, it's written on x cubed. So we have to divide both sides by negative 1, because that's negative 1 times x cubed. We have to divide by negative 1. And now we can see that this is really just reflecting across the x-axis. We'll draw the parent graph, and then we're going to reflect across the x-axis. So we're going to use red just because that's what we typically use for reflection, not that it really matters. And whoops, I forgot to write the equation that we just graphed. Alright, so if you got that one right, good job. Let's go on to number 24. Here's another situation where you really have to be careful. What this means is y is equal to negative 1 times 4 to the x. You can use parentheses on one or the other. But in order to put that negative 1 on the other side of the equation, we have to divide both sides of the equation by negative 1. So we have negative y is equal to 4 to the x, and now we can see that all we're doing is just reflecting across the x-axis. So the parent equation is the following. This is a exponential parent relation, so we have an asymptote on the x-axis. Plug in 0, we get 1. Plug in 1, we get 4. Connect the dots. And again, we're just writing a negative on y, so that means we're going to reflect across the x-axis. So our graph would look like so. All right. I want you to try number 25. Use number 24 to help you, and when you come back, we'll do it together. All right, we're back. So same situation. We're going to divide both sides of that equation by -1. And we get -y is equal to 3 to the x. Obviously, the parent relation is y is equal to 3 to the x. We have a horizontal asymptote. This is an exponential relation. Plug in 0, we get 1. Plug in 1, we get 3. Connect the dots. And there you go. But now we're going to graph -y is equal to 3 to the x. So that's going to reflect across the x-axis because we're writing a negative on y. Remember, it's always the exact opposite of what you would think. So if you got that one right, excellent. Good job. Okay, now we have kind of a special situation here. You know that when you write a negative on x, you reflect across the y-axis, but it doesn't seem like we have that situation here. But remember, if you have a negative symbol on a fraction, you can write it in the denominator, or next to the fraction line, or in the numerator. It's the same expression. So what we're going to do is we're just going to take that negative and bring it down to the denominator. So now we can see that this is just reflecting across the y-axis. In this case, it just so happens that when you reflect the reciprocal parent graph across the y-axis, you get the same graph that you would get if you reflect across the x-axis. So it doesn't really change much, but still, this demonstrates the principle that you can just move that negative down into the denominator. So that's the parent graph. Now we're going to graph y is equal to 1 over -x. So our asymptotes don't change positions, but we're going to reflect across the y-axis because there's a negative on the x. So we're going to reflect across the y-axis. So these points are going to be reflected over here, and these points are going to be reflected over here. So we'll get the following graph. So you have the same situation pretty much on number 27. The only difference is instead of the negative being written in front of the fraction line, it's written in the numerator. But again, you can just change that negative or move the negative symbol so it's down into the denominator. Then you know you're just writing negative on x. And that means that it's a reflection across the y-axis. So it's really just the same problem. But I want you to get the general idea here. I want you to do this. It seems like an easy problem, but I want you to get this problem done so that you can solidify these ideas in your mind. So try 27. When you come back, we'll do it together. Okay, we're back. So again, I'm just going to take that negative in the numerator, and I'm going to throw it down into the denominator. So it's the exact same problem that we just did. So I know it seems kind of tedious to have to do the exact same problem, but you really need to understand these little details about the math notation. This is really just about math notation when it comes to a lot of these problems. So we're now going to graph y is equal to 1 over -x. And that just means we flip our points across the y-axis. The asymptotes don't change positions, and we'll just connect the dots, and there we go. That was kind of a sloppy graph, but if you got that graph, good job. Okay, let's go on to number 28. We have a slightly more complicated equation here. and you can see that we're subtracting 4 from x. That tells us to move the parent graph 4 units to the right. But we're also subtracting 3 here from the absolute value of x minus 4, and we don't know what that tells us to do to the parent graph. So you know what we're going to do. We're going to add 3 to both sides of the equation. And that's going to put the 3 on the other side of the equation. And now you can see clearly that we are subtracting 4 from x and we're adding 3 to y. So this is going to be a translation. So let's start with the parent relation. That's obviously a absolute value relation. Let's write the equation. And of course you know what that looks like. That's the V-shaped graph. I didn't draw that perfectly, but you get the idea. And now we're going to translate. So we're going to replace y with y plus 3. And we're going to replace x with x minus 4. And that's going to move the graph 4 units to the right. So 1, 2, 3, 4. And 3 units down. 1, 2, 3. So there you go. All we had to do was just change the form of the equation and we could see exactly what's happening. So again, the most important thing to understand is that it's up to you to change the form of the equation so we can see what's happening to the parent graph. Okay, let's try another one of these. You can see we're adding 3 to x. That means move the parent graph 3 units to the left. But what about this 2 here? We don't know what that 2 is telling us to do. So again, you know what's going to happen. We're going to rewrite the equation. And we're going to somehow move that 2 to the other side. Now, obviously we have parentheses here, so that means we're multiplying x plus 3 squared by 2. So we're just going to divide both sides by 2, and we get y over 2 is equal to x plus 3 squared. And now you can see that we're adding 3 to x and we're dividing y by 2. So this is obviously a translation and this is a dilation. So let's write the parent equation. That's y is equal to x squared. Let's graph the parent graph. Okay, and we can dilate first or we can translate first. I think I'm going to translate first. So I'm going to replace x with x plus 3. And what that does is it moves the graph 3 units to the left. So all points are moved 3 units to the left, and there we go. Okay, then I'm going to dilate. And you don't have to use these colors, like I said. Don't get carried away with colored pencils or colored pens. This is more for your benefit to see what's going on here, but you don't need to have these colors when you're doing your homework. Okay, so replacing y with y over 2 means you're going to multiply all the y values by 2. So the y value of this point here is not going to change, that's 0, but multiplying by 2, those points are going to move up, and the other points are going to be off the window, it looks like, so we can just connect the dots. So there you go, that's the graph. It doesn't have to look perfect, just as long as it's the bottom part of the graph is a little pointed. Sorry about that. It's not supposed to be so pointed, but there you go. Okay, let's move on to number 30. Let's do one more of these before you try one on your own. We have x multiplied by 3. That means you're going to have a horizontal compression. You're going to divide all the x values by 3. Remember, it's the exact opposite of what you would think. It's not multiplying x values by 3. You're going to divide all the x values in the graph of the previous equation by 3. But what about this negative here? What does that mean? Well, again, we don't know what it means. We have to put that negative on the other side of the equation. So I'm going to rewrite the equation. And it's so important to understand that this expression means negative 1 times 4 to the 3x. That's what that means. When you write a negative in front of an expression like that, it means you're multiplying negative 1 by the expression. A lot of students get really confused by that. And that's the purpose of this math course. That's really the purpose of every math course, is to make sure that you're not confused by the notation. That's the primary goal of every math course. So now let's divide both sides by negative 1, because that's the opposite of multiplication. We're multiplying here in yellow, but to get rid of that multiplication, we're dividing by negative 1. You can multiply both sides by negative 1 also, but just to keep it simple, we're just going to divide. And of course, if you divide any expression by a negative, it just makes the expression negative, or the variable in this case. So now we can see that we are just writing a negative on y in the parent graph. So now we know what to do. So let's graph the parent graph. So this is an exponential graph. Obviously, there's a horizontal asymptote. Plug in 0 for x, plug in 1 for x, and find the y values, and we can see that this is the graph. Then we can dilate or reflect. I'm going to reflect first. So we're going to replace y with negative y. And when you write a negative on the y, you reflect across the x-axis. Remember, it's the exact opposite of what you would think. So we're going to reflect across the x-axis. We have those same points, just flipped on the other side of the x-axis. Okay, so now we're going to horizontally compress. We're going to dilate. So we're going to replace x with 3x. And that tells us to divide all the x values in the graph by 3. Now, this is not going to be easy to really show this on the graph, but sometimes you just have to deal with these situations. So this x value here on that point is 0, so that's not going to change positions. But the x value of this point is 1, and we're going to divide by 3, so it's now going to be 1/3. And let's see if we can plug in any other values. It doesn't look like other values are going to be easy to find, so we can just connect the dots, and there you go. So that was a horizontal compression, meaning we pushed the graph inwards this way, and we pushed it inwards this way. Okay, now it's time for you to try. You can take a picture of these previous problems with your phone if you'd like, to help you. And I'm going to leave 30 in the window. Go ahead and try number 31. And when you come back, we'll do it together. Okay, we're back. We're subtracting 1 from x. That means to move the parent graph 1 unit to the right. But again, this 2 here, we don't know exactly what that tells us to do. So we're going to subtract 2 from both sides of the equation. And the new form of the equation is the following. And now we can see exactly what to do. So let's write the parent equation first. Obviously it's the square root relation. We have the reference points 0, 0, 1, 1, and 4, 2. Connect the dots. Those are all on your library of relations. And we can see that we're, let's write the equation first. We're moving the parent graph 1 unit to the right and 2 units up. So now we have the following graph. So there you go. So if you got that one right, good job. Okay, let's go on to number 31. Go ahead and, or actually this is going to be 32. Try number 32. And when you come back, we'll do it together. All right, we're back. We have a negative on x, which means we're going to reflect the parent graph across the y-axis. But we don't know what this 4 here tells us to do, so we're going to add 4 to both sides of the equation. And that's going to cancel out the 4's on the right side of the equation. And we see that we have the cubic parent relation, so let's go ahead and graph that just for our reference. Okay, and we can see that we're reflecting across the y-axis and we're moving the graph 4 units down. So in this case, you can actually do either. It doesn't really matter which one you do because the operations are separated on each side of the equation. So I'm going to reflect first. So we're going to replace x with negative x. And when you replace x with negative x, you reflect across the y-axis. So I'm just going to flip my points over the y-axis. And then we're going to replace y with y plus 4. So I'm going to use my orange color for that. We're just used to orange for translation. So that means I'm going to move the graph down 1, 2, 3, 4 units. And we need to count out 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 to find another point there. That's because I'm using the previous graph there. If you plug in 2, pretending that this is the origin, you get 8. Whoops, that, yeah, that's the right point. So there you go. My graph wasn't perfect. Maybe I should redraw that. Your graph doesn't have to be perfect, but again, it doesn't have to be perfect. Okay, so if you got that one right, good job. On to number 33. Go ahead and try number 33. I think this will be the last problem for today. And when you come back, we'll do it together. All right, we're back. So this 2 here tells us to divide all the x values by 2 in the graph of the previous equation, but the negative here, we don't know what that tells us to do when transforming the parent graph. So it's also important to understand that that negative in front means negative 1 times log base 2 of 2x. It's multiplication. You're multiplying by negative 1. A lot of students have trouble with that, so you need to realize we're going to divide both sides by negative 1. That's the opposite of multiplication. So dividing both sides by -1, we're going to get negative y is equal to log base 2 of 2x. Because the division cancels out the multiplication here. So we have obviously a log base 2 parent relation, and with logarithmic graphs you have a vertical asymptote. 1, 0 is always a point that works regardless of the base. Then if you use the logarithm properties, plug in 2, because that's the plug in 2 for x because that's the base, 2 is the base. When those numbers are the same, you get 1. So out 2, up 1. Plug in 4, that's a power of 2. And because 4 is 2 to the second power, you get 2. Again, logarithm property 2 down in the middle there, it tells us that if you plug in 4 for x, well, 4 is the same thing as 2 to the second power. And if these bases are the same, you see these purple bases here, if they're the same, that means the value of the logarithm always ends up being whatever that exponent is there. So you plug in 4 and you get 2. And I think that's the only points that we can fit on the graph. Okay, so again, we have a negative over here and we have a 2 multiplied by x over here. So because they're separated on either side of the equation, you don't have to worry about the order that you transform. So we can reflect first or we can dilate first. I'm going to reflect first. So when you write a negative on the y, you reflect across the x-axis. So I'm just going to flip these points over the x-axis and connect the dots. And I can't forget to draw my vertical asymptote. And then we're going to multiply x by 2, or replace x with 2x. And it's very important that you use parentheses when you do that, just to avoid any confusion. So now we're going to dilate the graph. When you multiply x by 2, that divides all the x values of the points of the previous graph by 2. So this point here, that has an x value of 1, so it becomes 1/2. This point here has an x value of 2, so divide by 2, we get 1. So all the y values are staying the same, we're just changing the x values. And this point here has an x value of 1, 2, 3, 4, so that new x value is going to be 2. And now let's see if we can plug in an x value here that will give us a power of 2. I think we can plug in 3. If we plug in 3 for x, we get 8. Then you have log base 2 of 8. I'm just writing x equals 4, so if x equals 4, we get log base 2 of 8. And then 8 is the same thing as 2 to the third power. Now using this property over here, logarithm property 2, we know that the value of that logarithm is just whatever that exponent is. So if we plug in 4, you see this green 4 up here, if we plug in 4 for x, we get 3 for that logarithm. But don't forget, we have a negative y over here. So we get negative y is equal to 3. And so y is equal to negative 3. So if we plug in 4 for x, we get negative 3. And I think those are the only points that we can really plot that are going to be on our window. They're easy to find without a calculator. So I'm going to connect the dots. And I can't forget to draw my asymptote. You should do that probably first before anything else. Alright, so we horizontally compressed the graph. So if you got that one right, excellent. So that was the class today. If you'd like to take screenshots or pictures with your phone of the work that we did, you can go ahead and do that now. So here's screenshot number 1, screenshot number 2, and screenshot number 3, and number 4, and number 5, and number 6, and number 7, and number 8, and number 9, and number 10, number 11, number 12, and number 13, and number 14, and number 15, and number 16, and number 17, number 18, and number 19, but don't go before you get your homework. Let's see what the homework is. Now, you don't have to show the algebra when you change the form of each one of these equations. So what you can do is just complete the operations on the equation in your head and write the result over here. This is going to be your final equation that you're going to graph. And of course, you're going to need to write the parent relation though, the equation and the graph. So go ahead and get screenshot number 1 of the homework. And screenshot number 2. And number 3. And number 4. And number 5. But don't go before you get the answers. Let's take a look at the answers. Here's screenshot number 1. And number 2. And number 3. And number 4. And number 5. Remember, if you don't get that homework done, it's 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.